All right, good afternoon, everyone. I'm going to wrap up the last of our discussion from last time on kernel models. If you guys remember, we looked essentially at these kernel models that are doing these local regressions where you look kind of like with the k-nearest neighbors, you are deciding this bandwidth window in which we're actually looking and considering points that are kind of close by or farther away. And we saw right at the end, let me see if this works. Oops. Figure margins too large. All right, let me try this again. No. Okay. Okay, so we have our data here. Okay, and let me just pull this over. And we were able to look at a bunch of different kernel models, right? So this is the actual fit versus when we had like a good bandwidth versus when we decrease the bandwidth too much so that you start to get some overfitting. Hopefully you guys can see that, right? The line becomes more and more squiggly. And then ultimately, you know, you might start to jump from point to point as you see kind of happening here. And then in the other direction, right, as you increase the bandwidth, it's kind of averaging over more and more points. And you have essentially what ends up becoming a straighter and straighter line until at some point, if you consider the full window, you're essentially looking at the average across the full set of points. Okay? Let me see if I can do this one more time. No. All right. Okay, and so here, so you don't need to follow along. This is demonstrating, you know, if we wanted to do it in the cross-validation way that we've done before, I can rewrite the function, our sort of manual cross-validation function that I showed, and do this whole training testing thing to obtain a bunch of cross-validated mean squared errors, and then you pick the lowest one with the lowest out-of-sample mean squared error corresponding to particular bandwidth across a range of bandwidths that I'm testing to arrive at kind of the correct one. And so this, oops, what's going on here? Yeah. So I'll leave this code as reference so you guys can see explicitly how we do this. We arrive at kind of our best CV result. And let me get rid of this. and this is as per our validation procedure, kind of the best that we can do. So that's one way of doing it manually, which accompanies, I think I showed at the end of class that you could actually use the built-in cross-validation mechanism in the kernel regression to do the same thing. Let me just pull up that code just to make sure we have that as well. No, that was for the smoothing spline model. Okay, so this is the kind of built-in way that you can do it manually. I'm sure there's a package that lets you do the cross-validation kernel bandwidth selection, but not in this default one that we're using. Okay, so difference in approach between the local regression that will get you this via kernel regression as one of the examples of local regression versus doing the spline-based approach. And I talked about kind of the strengths and weaknesses of both of those last time. Any questions about that? So one of the things that I want to reiterate, right, is that as we're doing these either semi-parametric or non-parametric approaches, there are no longer coefficients for us to interpret, right? There's nothing that gives the same level of interpretability as our linear regression. And that's the trade-off that we make in being able to do something that will be a lot more flexible in the functional fit and gives us the ability to do these crazy curves, but that no longer provides the sort of ease of interpretation that we had before. Okay, however, there are some hybrid approaches that people have come up with that try to retain some elements of interpretability, but still give us flexibility that like these non-parametric models or semi-parametric models give us. So we're going to look at that to start off today. So we are going to start off by looking at what is known as a general additive model, also known as a GAM. And so this maintains some interpretability by additivity of terms. So this uses a spline for each individual variable and adds them together. Okay, so let's suppose that I have some equation that we represented traditionally in our linear model like this. Okay, so this is our regular linear equation. And in a GAM, we do something like this. Where this is our smooth spline function. And actually, it's more generic than this. You can leave some variables as having subjected to the spline, and others you can leave as just in the sort of traditional linear form. So I'll show us what that looks like in just a moment. Yeah, I think the easiest way to demonstrate this is just kind of through example. So let's walk through. Let's walk through an example of this. All right, so jumping over here, we are going to look at a general additive model or GAM example. We're going to use the ISLR library again because it contains a data set called hitters, which we'll load in. And then we're also going to use a library called MGCV, which is the package we need for the GAM regression. So before I run into this, let's take a look at the hitters data set. Okay, I'm not a baseball person, so I don't know what all of these stats are, right? But these are stats related to, so this is a baseball data set, and these are stats. Each row corresponds to a player in the MLB and statistics associated with I think our particular season. So there are number of runs, number of walks, how many years the person has been in the league, and so on. What league division, and salary here. So we want to see if, well, not if, but how a lot of these statistics are related to their salary. Okay, so I'm going to start with the linear fit first. So linear salary, and the variables I'm going to include are at bat, hits, walks, runs, or I should say, yeah, C runs, C RBI, C walks, the division they're in, and putouts. And this is all coming from the hitters data set. Okay, I can do a summary of this. And this will give us, yeah, what we expect, right? So a bunch of different variables, and these will tell us the relationship between each of these statistics and their salary in thousands of dollars. So at a base level, you know, they would be expected to make $117,000 a year. And then, you know, the more hits and walks, the higher their sort of corresponding salary by $6,800 and $6,400 respectively. Some are negative. And then, you know, if you're in a certain division, you make less on average. So At this point, you guys should all be pretty familiar with this. And remember, one of the assumptions that we make in the linear model is that the relationship between all of these are linear, right? So for every additional hit, you make $6,850 more. And that's a linear relationship, and same with all of the rest of the variables. But let's suppose that that relationship in reality isn't totally linear. We can actually investigate this with the GAM. So what I'm going to do here is, in the GAM, we set it up actually the exact same way, except that I can put in an S around each of our variables that we're interested in adding the smooth spline to. So let's do that. To every single continuous variable. We can't do splines on discrete variables, so the division variable is going to stay the same. But we can do it for everything else. Oops, I'm putting C here. Should be an S. SCIBR, S, C walks. Plus division plus S putouts. Data equals. Okay, so we run the model, and now let me take a look at the summary. And we're going to see something kind of interesting here. Significance of smooth terms, and they give this like EDF value and then some p-values here. The EDFs are not the coefficients. They are not interpretable as such. And actually, we still actually have our parametric coefficients here, the ones that we didn't smooth, so our intercept and our division, and now they look pretty, well, the intercept looks pretty different. I think the division is actually pretty close to what it was before. So negative 120, so still negative 120 here. Okay, so what are all of these spline smooth terms? So we can look at this by doing this. No. Okay, I need to. It's really annoying that the figure margins mess this up. Okay. One more time. No. Okay, what if I do this? All right, 1 second. I don't know why this happens just after so many years of working. Okay. Make this even bigger. Ah, okay. Oh, you know what? Maybe we can do it like this. All right. Now we'll do it on one page. Okay, so what are we looking at here? Can I scroll through these? No, I can't. Okay, we'll keep it on here. Okay, so what we have on this plot is a spline smooth between a particular continuous variable, one of the x's, and our y, right, which is the salary. Actually, if I go back here, that one's not as... These are 7 variables that are smoothed individually and that you can essentially add up. So if this were a linear regression, each of these would just be a line that would show the relationship between my x variable and the y variable of salary, and that line would represent the coefficient in the beta. But because we're doing a spline smoothing operation, now we no longer have a coefficient, right? We have something that can be more flexible that displays the relationship between any of the variables and y. So that's what this is showing. Each of these little tick marks down here is like the location of one of your x data points, okay? And you end up with a curve that looks like this with standard errors around it, like so, with a dotted line, okay? So you tend to be a little bit more confident in the sort of estimation in the middle, and then as you have kind of less data points at the ends, that error band gets larger. Does this look like a straight line? No, right? It's kind of increasing at first and then decreasing. And so this is actually a really good way to test the linearity assumption in your linear models. So say you wanted to just do, you just wanted to do a linear regression. At the very least, you could run a GAM to see whether relationships are truly linear. And in some cases, it would be a pretty bad assumption, right? Like this one that we're just looking at, okay, it doesn't appear to be totally straight, but maybe, you know, a straight line would fit inside of the error bars, and so you could maybe reasonably argue that it's okay. But for something like this, right, where the trend is definitely a little bit more clearly parabolic, that assumption maybe less defensible. Okay. And here you have it pretty flat before it kinks kind of upwards. Here it flattens out kind of later at the end. CRBI may actually look relatively linear, so that might be one that you could leave. Probably not this one. And putouts actually looks fairly linear as well. Okay, so the GAM basically lets us apply splines to individual variables and then have them included additively into the model. Okay, and so if I were to pick a particular X point, or a particular row of data corresponding to one player, they'll have a putouts number, they'll have a CWalks number, a CRBI, and so on. I could go back in, figure out where I am on my fit curve, add it all up, and then you would get our final salary, right? Okay. So if I were to think about my GAM fit where I double checked the fits and I saw that, what did I say? So CRBI and putouts both appeared to be linear. I can go back in here and let's just get rid of the splines for putouts and let's get rid of the spline for CRBI. Run the model again. And in the summary, right, I know that here now I can get the beta coefficients that are interpretable as before, leaving these linearized because of what I saw in my previous plot, combined with spline versions of all of the other variables, right? And we can always see what the corresponding fit looks like with those guys, right? And so this would be these would be the fits of each individual variable against my Y salary. So here, and they'll look pretty similar as to what they were before. Okay? Any questions about the GAM?
For the variables that we obtain from the spline, do we always need to look at the graphs to see the exact relationship between the the independent variable and the corresponding dependent?
In order to you're asking, is that the best way to see whether or not there's linearity?
To check out say if the hits is 100, then do I need to look at the graph to see the corresponding the salary when someone's hits is 100?
Oh, no. You could just do the predict function, right? You can actually predict on individual spline fits to see essentially what it's saying about the corresponding value. And so if we're talking about hits, for example, let's go here. So you're asking, do I need to plot this explicitly to be able to say at 100 hits, the fit is telling me that I should be at this value of Y? No. So you can you can actually predict on the particular function, the spline function, to get that number. How do you do it individually? Actually, I'm not sure how you would do an individual one, but you definitely can. You may have to. Yeah, there's probably some option within the GAM function that will let you point to a particular one to do a prediction against. But yeah, otherwise, there isn't an easy equation or value, right? There's no like coefficient value or easy equation that would let you predict the output, the response variable. You'd have to kind of automate it through the estimated function from the GAM fit. Make sense? Yeah. Yeah, so hopefully that's clear for everyone, right? We no longer have access to betas. Instead, we have essentially this line, but the GAM is arranged in such a way that it's additive, and so each individual variable is connected to our outcome via this this spline fit. And so at the very least, we could visually see or do some kind of prediction to get a particular value that we're interested in. Okay. Any other questions? All right. So, yeah, that wraps up our discussion on our sort of foray into nonlinearity, and we will touch back into this once we get to neural networks, which are a sort of more advanced version of this, where why is it that I'm introducing this concept of splines and local regressions, and getting us to think outside of some of the constraints of a linear regression. Why is it that in the direction of predictions, which is what these things are good at, why aren't splines and other types of local regressions maybe more widely used? Why did we go to kind of neural networks as the kind of like big hot topic in machine learning? And that has to do with scalability. Okay, and so with these models, they're very powerful, very flexible, as we've kind of demonstrated. But as you have more and more data and more variables, or machine learning people like to call them features for some reason, as you have more of these variables, the ability of these models to quickly estimate fits to do prediction is a little bit unwieldy. And neural networks, it turns out, are a very adaptable model for large-scale application. And that's why you probably don't see this type of stuff done as much in the machine learning world and in the predictive world as some of these other modern methods that we're going to be covering later on. Okay? All right. Any other questions? Yeah.
Can you just explain again when you would move to a GAM rather than the kind of like breaking splice kind of model that we talked about last time?
Yeah, so because the splines don't give you any ability to do interpretability, what the GAM does is it splits up the variables in such a way that it's all additive back to your Y. so that you can look at these individual plots and understand those like one-to-one relationships. So when do we use a GAM? It's kind of like if you want to maintain some of the interpretability of linear models, but that maybe you're worried about the functional fit and the functional relationship between your x's and y's. And you're like, well, I don't think there's actually a linear relationship, but I don't want to go fully into like a non-parametric model where I no longer am able to interpret. I'm mainly able to do prediction. So when you're doing nonlinear fits, but you want to maintain interpretability, that's a good time to use a GAM. And I'll actually also maybe amend that by saying, even if you're doing a linear model, you ought to run a GAM to test your assumption that the fit is linear, right? So you do, y regressed, x1, x2, x3 regressed on y, and you just want to run a linear model. You should probably run a GAM first and make sure that x1 and y, x2 and y, and x3 and y are actually relative. It's rare that you'll actually get a real straight line, but if it's like relatively linear, you can be like, okay, it's probably fine. But if it's not linear, then you'll know when you see these GAMs, right? When you see something like this, you're like, that's definitely not a linear relationship. So I either need to transform the data or, do something else, right? Or retain the GAM. So that's the other case. I would say doing linear model, run a GAM, make sure, just double check about that relationship. Okay. Any other questions? Okay. So the rest of the day, we are going to talk about kind of a special case of nonlinearity, and actually not even necessarily nonlinearity. Special case that I ended up putting this lecture together 1 or 2 years ago, kind of based on popular request. The special case being time series data, right? And so this is something that I think folks work commonly enough that there are a number of techniques and approaches and sort of philosophy on that is kind of worth discussing as its own sort of topic. So time series, and I would describe this as, much like the rest of this class, kind of introduction into some of the primary concepts behind time series modeling. If you want to get more into this, there are actually entire classes that you can take focusing on time series techniques and more things to get into. So time series is a common but special case of statistical modeling so this talks about the obvious correlation introduced by sampling points adjacent in time. This can restrict the applicability of many conventional statistical models. Okay, so let's talk about classical regression for time series. So we have something like yt is equal to beta 0 plus beta 1 xt1 plus beta 2 xt2 and so on, beta n x tn plus epsilon t. So if I have a table, t, y of t, x, t1, and so on. Okay, so maybe I have time periods 1, 2, 3, so on, A, B, C, D, E, F. Okay. So the idea here is maybe I have some kind of relationship that's correlated over time, in addition to our kind of direct relationships, right? And so suppose there's some kind of information that tells me in a particular time period, maybe that is connected to variables in the previous time period. Maybe the variables themselves might be connected. And so our sort of traditional regression, you might want to think about doing something with lag variables to represent these kind of relationships. So maybe beta 1 xt1 ... plus, let's say, something like yt minus 1. So this would be known as your lag variable. Okay. So let's talk about some of the sort of concepts behind this, some of the pitfalls in doing something like this, and then we'll show some examples. Okay, there's kind of hidden behind this an idea known as stationarity. Okay. This is a critical concept for time series because it ensures statistical properties such as mean and variance stay constant. And that is necessary for many modeling assumptions. So if you have mean and variance that is changing across your range of data, that can bias your model. So consider something like this. Maybe this is like stock price versus time. You could have this upwards trend. And so in this case, model may predict continuously increasing prices even when conditions differ. Right, because you have this like constant trend that's going upwards, it's difficult to disassociate effects of different variables from this particular trend. And so ideally, you would want to essentially do this, apply stationarity in some way in order to disentangle that. And we'll talk about different ways of doing it in just a moment. But maybe one of the first things, to point out, so why can't you just add variables to control for the trends, right? So a lot of the ways we think about dealing with this ordinarily is essentially adding additional variables into the model in an attempt to control for that sort of upward trend, right? So the sort of fundamental statistics answer to this is many models require stable means / variance to operate properly. And so what this tells us is that kind of no matter how many variables I add into my regression equation, you can't get rid of the unstable mean problem. And so you'll never really get rid of the bias that's introduced from this particular, the feature of this data set. Secondly, this can lead to unstable models over time, which lowers predictive power. And 3, you always risk multicollinearity, and importantly, overfitting, right? So we've talked at length about if I just throw more variables into the model, running into this issue of overfitting. And maybe including all variables is simply not possible. Okay. So I'm going to show I'm going to start off by showing an example of this. So that we can kind of explicitly see what I'm talking about. Set seed is a function in R that that specifies when you do random draws that you're drawing from a specific seed. So usually when I do like R norm or something, we all will get different answers. But if you set seed first, it'll make it so that we all get the same thing. And for a time series, I'm doing this because, the answer could get wildly different because we are compounding, as you'll see in a second, compounding the data. So this cum sum stands for cumulative sum, cumulative summation. This is the values get added to the previous values, right? And so there's a direct dependency on your current value based on your previous value. So fundamentally, we're essentially generating this sort of time series data. We're going to fit, as an example, 3 regression models. We're going to do our raw model, which is just y regress on x. So this is kind of the most naive model. What are some ways can you guys think of that might deal with this idea of stationarity? So let me actually run this and then plot it. And can I do this? Oh no. It has to be in order. Okay. Here we go. So I can do it like this. X type equals L. Lines Y. Here we go. So we have our X value in black and our Y value in red. And I want to apply stationarity. Does anyone have any ideas on how I might be able to do that? No ideas at all. Okay. It's actually a little bit harder than you might think. One way that you might try to do this is by demeaning. Okay. So this is where for every individual point, I just subtract away the average across all of the data. And so here, we're going to do something like this. Oops. Where I demean both my x's and my y's. And it turns out demeaning is not actually the best method or an effective method of applying stationarity to your data. The most common method is actually to do a differences. And we're going to talk about this in a little bit more detail in a second, but I'll just show what it's going to look like after you do stationarity through differencing. And differencing just means I take y of t minus y t minus 1, and then y t minus, or t plus 1 minus y of t, and then y of t plus 2 minus y of t plus 1. And you can do that with this, which is known as the diff function. Okay, so if I look at the summary, we're going to see some pretty different things. So let's take the naive model. We see a really statistically significant effect of x on y. And actually, before I go there, what is the relationship between x and y? So this is another example of the data generating process where I got to decide where y comes from and where x comes from, right? And so we've done this before where we do these samples, and then, I'll set y equal to some value of x, 0.5x, all the way to that weird sine cosine thing that we did last time. What about in this example? How is x and y related? It's right here in line 104 and 105. Yeah.
Are they the same?
No, actually, it may look like that because I'm using the same line, but we're doing random draws. So actually they're completely unrelated, right? There's no x. Y is not a function of x. It's just random draws, right? Is everyone following? So what we see here, we actually know to be not true. It's statistically significant. Not only that, you have a decently high r squared. Well, I guess that's not that high, but indicating at least probably this relationship. And let's look at the demeaned version. Here again, we have almost identical relationship, 0.505, similar r squared, even though we know that they're not related. And then when we do the difference, we can actually see that there's no relationship between x and y. Okay, so let me show you what this looks like in the plot. Let me. So the plot on the far left, the top and bottom, the top shows our x in black and our y in red. Then we see below that in our naive regression, when I plot the x's against the y's, there is this linear relationship between the two. Now, if I apply a transformation to the data so that I demean it, so I subtract away the mean of the value across y and across x from each respective data point, we get the middle one, where the black is the demeaned x values and the y is the demeaned red values. And you see it doesn't really do anything. It's still, the relationship ends up being kind of the same when we look at the demeaned x values against the demeaned y values. Okay. Lastly, we do the difference values, where you do x of t minus x of t minus 1, and same for y of t minus y t minus 1. That removes essentially the time effect from our data. And from there, we can see when we run the regression that there is no longer any relationship between our x and y. Okay? Which we know to be the truth based on the way that we generated our x and our y's, right? So if you think about the way we actually generated the x and y's, is we force them to be related via, to each respective past value based off of this cumulative sum function. And the differencing is what eliminates that relationship. And once you do that, that gets rid of, or the stationarity that then gets applied in the differences allows us to better understand the relationship between x and y, which we know to be non-existent. Okay? Any questions? All right, so let's talk in just a little bit more detail about differencing. So what we just did, so this is known as differencing in time series. So the first diff is delta y of t is equal to y of t minus y of t minus 1. And you do this for xt as well, xt minus xt minus 1. And essentially you do this for each variable. You can actually, so what we did was the application of one difference. You can actually continue doing this. So can continue differencing if non-stationarity is still present. And you could do other versions of differencing if you do like seasonal differencing, for example. There are other patterns of differencing, but the most common is just to do this like period against period differencing. So what this ends up looking like, so y of t is equal to beta 0 plus beta 1 delta x1 of t plus beta 2 delta x2 comma t, so on and so forth, beta n delta x n comma t plus epsilon t. So the beta corresponds here to a change in response to a unit change in x, so rather than absolute levels. Okay? So the stationarity, essentially, this helps with keeping the mean and variance in the model constant for things that are essentially autocorrelated, right, over time. And so differencing is just one of the ways to apply stationarity. There are many other approaches that you can take. This is probably the most basic one. So just kind of introducing this as a concept to deal with the particular problem of stationarity. Okay. Okay. Any questions with that? Okay, so we're going to look at something else now in time series. So this is known as moving average in time series. So this is not to deal with stationarity. I'll talk about the application of this in a moment. Let's first discuss the algorithm. So we choose a window size. So k period. And then we apply a moving average, also known as MA, for each variable. That'll look something like this. So note this is our moving average variable, and then we can fit a regression model. MA T of y equals beta 0 plus beta 1 MA T x of 1 plus beta 2 MA T x of 2 and so on. Up to beta n MAT xn plus our error term. Okay, So that is an example, sort of a easy application of moving averages. And to kind of be a little bit more explicit of the difference, so differencing versus moving average. So this is focused on dealing with stationarity, removing trends / cyclical components, whereas this is focused on smoothing to reveal underlying trends. Okay, so slightly different purposes. All right, any questions about this? Okay, so let's look at this, an example of moving averages. We're going to use a library called FPP to do this. This is a package commonly used in time series that includes the ability to do some of these moving average calculations. So we're going to set our window to 5. So this is our window size. And this is a way we're kind of manually replicating what I was showing in the equations. We'll have these weights that essentially will do our averaging for us. So we'll do the moving average of y. We can do that by doing filter ma.data $y weights sides equals 2. Sides refers to when I do the moving average, if I'm looking only in one particular direction or in both directions. So if I have a window of 5 and I'm looking at both sides, then I will be doing 2 periods in the future. So period 2, period 1, 0, the current period, the period before, and then the period 2 before. So that would be a total window of 5. Okay, so we create each of these guys. Oop. I need to, sorry, I didn't even generate the data yet. So let's do this. So we'll have 100 time periods. X1, we're going to do similar type of thing here. And here we are relating our x's and our y's. Okay, so let's run all this. So we will have, where's our MA data? Okay, so we have our time, our x, which is a cumulative sum of random variables, x2, cumulative sum of random variables, and y is a function of x1 and x2. Okay, so if I take the average of, so I have 100 time periods, right? And I'm doing this moving average where for each of my x1, x2, and y, I want to look 2 periods into the past, 2 periods into the future, and then including my current period, I average that to come up with a new value. How many moving average values do I have for y, x1, and x2 across the 100 points? Okay. Volunteer real quick. Oh, yeah, David.
I'll take a guess. I'm going to say 96.
96, right. And how did we come to this conclusion?
The first two are ignored because, well, there's nothing before that. The last two are also ignored because there's nothing before that as well.
Yeah, right. So if I wanted to do y10, I'd look at y8, y9, y10, y11, y12, and I average that. But if I wanted to look at y1, I would look at y3, y2, y1, and then I don't have data for things before that. So if I look at the data, the first two will be missing, right? Because you can't average against things that don't exist. And the last two will be missing because I can't average against values that don't exist. So that's one thing to be cognizant of when you're doing certain techniques here where you rely on past data. It will actually decrease the size of your data set, right? So for this, that doesn't seem to be too big of a deal. But imagine if you're doing a moving average with like 10 values and they're all looking in one direction, right? Then you drop like 10 data points. Okay, so that's just something to be cognizant of. We're going to just get rid of all of the data that's missing via this procedure. And then let's take a look at the data, what it looks like now. So I'm going to do x equals MA data $t. So we'll look by time at each of the variables. So x1, x2. Actually, why don't we also do this for just the non-differenced data as well? Oop. This is the wrong did not mean to put diff. I meant to put MA. Here. And here I want to just look at these guys. So what does this look like? So this is the raw data that's not mean. Oh, of course. So this is the raw data. We can see y as a function of x1 and x2, and then x1 and x2, where they are sort of heavily correlated from period to period, because we generated the data using the cumulative summation. And let's see what this looks like for once they are using the moving average. You'll see that the overall trends are a lot smoother, right? Because it's taking the average across these like moving windows. And so this lets us better understand kind of the underlying trends that are happening over time. Okay, and here we can run a regression model. Okay, and we can see that with the moving averages, we get pretty decent estimation of the coefficient values relative to what we know the true values to be, right, of 0.5. This is saying 0.48, and negative 0.3. This is saying negative 0.33. Okay. So the smoothing essentially helps with determining these relationships. Any questions? All right. So we will then look to our kind of final example for the day. And this is known as an auto-regressive model. So this assumes that the current value of the series can be explained as a function of past values. Okay, so y of t equals c plus yt minus 1 yt minus 2 and so on. Okay, and so these are the lag variables that I was describing. And you can add in not only the first lag, but multiple lags, kind of in the similar way as we were talking about the sort of differencing, right? And that the idea is that there is some correlation between our response variable and then previous time periods of the response variable. And in some of these artificial examples that I was generating, we definitely know that to be true, right? Because we're doing the cumulative sum function, and so we know that there's definitely some relationship between r, y, and the previous values. And so this is a very sort of powerful model to capture the effects of things changing over time. But this is kind of this is known as an AR. The autoregressive model, there are a lot of things to think about that we're not going to have really time to get into. And there are ways in which we can leverage this model and tie into things like the moving averages and combine them to get even more sort of powerful models. And we won't get into that today in our sort of overview of time series. Maybe one thing that I will talk about as one of the fundamental things to watch out for in autoregressive models is, this idea. So in our traditional linear regression model, we have this random error term, and we generally assume that that you have independence between here, right? Otherwise, if you have dependency between your error term and your x's, then you're biasing the model because there might be some unexplained variable that's actually leading to changes in y as opposed to what you're attempting to explain in x, right? And so that relationship is likely incorrect. You can imagine that this can really compound in a lag model. And so we really are worried about this issue of endogeneity as it relates to this error term. So let's take a look here. Actually, if I have... So y of t is equal to, let's say it's beta 0 plus beta 1 x t plus phi y t minus 1 plus epsilon t. So here, I can write this equivalently to xt equals beta 0 plus beta 1 xt plus so this times, well, okay, we'll do this times beta 0 so we have simply substituted in, let me, we simply substituted in for y t minus 1 the terms from this, if we were to turn this into here, and then looking at the previous previous terms. And actually, you would actually have also plus, you know, v2 of y t minus 2 here as well. Okay, so if you don't have independence here, right? If this term, sorry, if this term, I'm going to use a different color, were related to this, right? That means that you have this compounding problem that really gets magnified. And so the endogeneity issue in these autoregressive models becomes extra important to deal with. And so the ways that we, the ways in which you deal with this can be similar to the ways in which you deal with this in the traditional linear regression. So things like having like an instrumental variable can work, and they can propagate through time to like disconnect this issue. And there are a couple of other techniques which I won't get into, but just know that this is an area that you'll want to kind of be careful with. Okay. And note here, for our autoregressive, we need stationary data. Fortunately, some of the packages that are built in will essentially do that for you. So I'll show us a quick example using the ARIMA package. So ARIMA being a model that encompasses the ability to do autoregression. It actually includes, so the AR is the autoregression, the MA is moving averages. So this can actually combine a couple different models together. It's common to do both autoregression and moving averages together, but we're not going to do that right now. Using the data from before, do I have this set up properly? Hold on. 1 second. We'll just use the MA data without the moving averages. So MA data order equals C100. This order input for the ARIMA function, there are different components that you can add to it. The first one, where we're putting the 1, is for auto regression, how many lags that we're including. The last one is for the moving averages. I won't talk about the middle one. This is just if we're thinking about doing it with auto regression. And then in our ma.data, we're going to regress using our x1 and x2. Okay, and this should do it. Okay, and this will tell us the effect of the auto-regressive piece, and then the effect of the corresponding x1 and x2, which again we'll see as being relatively close to the values that were specified within here. Note that we don't actually have we don't really have an autoregressive element within our y. And so you end up not having something very significant here. But in an example where you do have the autoregressive element, that will tell us how that relationship compares. And note that it's a very powerful variable, right? Because the autoregressive element will contain the all of the previous terms explanatory variables, right? And so if y is related to not only yt minus 1, but to the x's in your previous time period, this autoregressive indicator will capture the effect of all of the previous terms on your output. Okay? Okay, any questions on this? Okay, yeah, and so just to reiterate, these are some like high-level approaches and concepts to think about in time series. We don't get too much into detail in this particular class, but if you're interested in doing more in time series, I'm happy to kind of point you in the right direction, either in material or other classes to take. There's actually a really nice, there are a couple nice resources on time series. If you wanted to study this independently, I can post them on Canvas. But otherwise, this is pretty much the most we're going to get into this particular topic. Just introducing a couple of concepts and models that you can use to employ in time series analysis. Okay. If there's no other questions on this, we'll end just a little bit early today.